Lesson 14.1, Counting Outcomes. This is the beginning of probability, and probability is just the number of ways things can happen and how we calculate them. The reason we want to calculate them is we want to be making intelligent choices. If we decide that something has a very rare chance of happening and we bet on it, we're going to be in big trouble. On the other hand, quite a few things have a very high chance of happening and a lot of people don't realize it. So we'd be wise to bet on those or just plan on those. Betting not being the best word to use. So go to a restaurant, it's got a limited menu. Got 2 choices for appetizer, 3 for the main dish, 2 for dessert. How many possible meals can you have? Well, let's just blast it out. We could have nachos. We could have wings. If I have nachos, let's just argue for a second. I have chicken, and then I have pie. I could also have nachos, chicken, and ice cream. I could also have nachos, steak, and the same choices, pie or ice cream. Could also have nachos, fish, and then pie or ice cream. But if I have nachos, those are only 3 choices I have with those 6 on the end. If I have wings, I'm in the same boat. I could have chicken, steak, or fish, and then I could have pie or ice cream, pie or ice cream, pie or ice cream. And I'll explain why I circled those in a little bit. Those are all the possible meals I could have. Any one of those strands starting from the N or the W and following it through, that's all the choices I have. And before we calculate the probability of something, we have to know how many possible choices there are, how many possible outcomes there are. This is called a tree diagram. You can see it kind of looks like branches breaking off left and right. However, if you look at the total result, which I circled over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, it's actually a very easy problem. To figure it out, we use something called the fundamental counting principle, which I really think is a great name. Feels like we're back in kindergarten. Everybody, we're going to learn the fundamental counting principle. 1, 2. It's a little bit more complicated than that, but not much. For appetizers, we had 2 choices. For the main meal, we had 3 choices. For dessert, we had 2 choices. To figure out how many possible choices, multiply them up. And that is what we got up here. 12 choices. This pops up on the ACT and it pops up in real life. When I get up in the morning, I think about shirts, ties, and pants. I have to figure out how many possible outfits I have, whether I need to go to the cleaners or not. Things like that. Speaking of which, if you have 3 different pairs of pants, 4 different shirts, 2 different pairs of shoes, how many different outfits can you wear so your students don't yell at you saying you wore that yesterday or 4 days ago or creepily like on April 2nd from 3 p.m. in the afternoon until 5 p.m. at night? It's kind of crazy. So the possible choices are 3 for pants, 4 for shirts, 2 for shoes. That's it. You have 24 different outfits, assuming they all match, which they never do. And that's the fundamental counting principle. We'll talk about that every now and then. Problem later today where we take it and tie it into another problem. Another problem, we want to put 5 different books on a bookshelf. Got our bookshelf, book A, book B, book C, book D, book E. How many different ways could I arrange them? And me, I'd put the biggest one first, but that's just me. Well, here's our first choice. All the books are available to us. We have 5 choices. And it could have been any book. Let's just, for argument's sake, say I put book C there. How many choices do I have now after I've placed book C there? Well, I have 4 choices. Let's say I put book E there. How many do I have now? 3 choices. 2 choices, and then the last one, I really don't have a choice. That's all I've got left. This is just one example. What's it multiply out to? Well, you need to go 5 times 4 times 3 times 2 times 1. 3 times 2 is 6. 5 times 4 is 20. That equals 120 different ways to do it. Notice it's different from the previous problem. We don't just multiply 5 times 5 times 5 times 5. We don't have 5 choices for each one. Once we use a book, we can't use it again. Hopefully you've seen that before, but if not, we don't have to worry about it. We call the solution to this problem multiplying a factorial out. The factorial is written with an exclamation point. 5 factorial, that's how we read it. I always shout it out. First time I get that in class, I say, it's not 5 factorial, it's 5 really loud, but that joke doesn't really go over that well. 5 times 4 times 3 times 2 times 1. And as we just saw, it equals 120. There's a button on your calculator for this. I won't even give you a hint. It's not that hard to find. Most people don't use it. They just go 5 times 4 times 3 times 2 times 1, which is totally fine. Factorials can be fun. There's a lot you do with them. This is equal to 4 times 3 times 2 times 1. I don't know why I keep writing that 1 in. 24. This is equal to 2 times 1. This is equal to 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And since I know that everything from 5 down equals 120, I only need to multiply 8 times 7 times 6 times 120. So if we had that for books, we'd have 40,000 plus choices to choose from. This one's tricky. I'm going to write it in different color. What is 0 factorial? It equals 1. And that bugs the heck out of people. That's a pure definition. There's no theory why it should do that. It has to do that to work because we'll have to divide by 0 factorial every now and then. We can't divide by 0. So by definition, 0 factorial equals 1. If you forget, just put it in your calculator with the factorial button. Pretty easy to remember that way. But 0 factorial equals 1. Here's a problem to use it. And, as always, things get more complicated. But I go to an amusement park with 9 different roller coasters. How many different orders can I ride all 9? So my first choice, I have 9 different coasters. Now, I've already gone on one. So my second choice is 8, then 7, so on. So it's basically 9 factorial. Which is a really, really big number. 362,880. It's a lot of different ways. Well, let's make it more complicated. I get to the park and I realize, you know what? We really don't have time. I'm only going to end on 6 of them. How many different orders? Well, what's the first choice? There's 9 of them. What's the second choice? There's 8 of them. Then there's 7 choices. Then there's 6 choices. Then there's 5 choices. And then there's 4 choices. But that's it. I'm out of time. I can only get to 6 of them. Only get 6 roller coasters. This is not 9 factorial anymore. It's 9 times 8 times 7. It's actually a way to do it with factorials. We're just going to keep it simple and multiply it out. $60,480. Significantly less, but still quite a few. This is just an introduction to probability, which you've already done, actually, to understand outcomes and statistical probability and observed probability, things like that. This will just give you a small taste of where we're going. Good luck.